Got it, year 13. Today we're going to have a look at another type of localized visual representation. So let's have a look at first example. So the first question says the distance from the modulus of z minus z1, which means the distance from z1 to z, is actually same as the distance from z2 to z. Now I don't know exactly what z1, z2 is, so I'm just going to randomly assume that z1 is here and z2 is going to be here. z1, z2. So it says distance from these two complex number to z are exactly the same. So the first thing that I can think of is if I connect these two, if I choose this midpoint, that tells me that this distance and this distance are exactly the same. So let's say this point is z. But is this the only point that will give the equal distance from z to these two complex numbers? You guys probably say no, there are actually many points, and those points can be on this straight line that actually passes the midpoint of z1 and z2 and perpendicular to the line z1, z2. So that's why we say that the perpendicular bisector of the line that connects z1, z2 is the loci that represent this condition or that satisfy this condition. So any points on this perpendicular bisector can be complex number z. Now, let's have a look at the second example with more specific numbers. Now, the second example says the distance from negative 2, 3i, so I'm going to draw negative 2, 3i, is equal to the distance from z to negative, 4 and I. I'm going to locate this point, 4 and I. So since the distance from the complex number to these 2 points are equal, so again, I know that it's going to be the perpendicular bisector and this straight line. So any points on this straight line can create the equal distance. From here to here is the same. I can choose any point. This distance and this distance is the same. So therefore, this straight line is the loci that satisfy this condition. Now let's have a look at the question 3. Now question 3 is slightly different. Now it's instead of having an equal distance, you're saying that one side distance is actually less than the other side. But again, you have to interpret correctly so that you can actually draw the picture nicely. So it says z, okay, we have to change this format from, put the brackets on, negative 2 plus 3i, because when we expand it, that will give us positive 2 and negative 3i. So z from this point is actually less than z from, again, I'm going to put the brackets on, so that we get 4 plus I. When we expand it, that will give us negative 4, negative I. So again, if you look at it, I actually just tweak the question from question 2. So again, I draw the same thing, negative 2 and 3i, and I have 4 and I. So we all know just now we had a perpendicular bisector that will give us an equal distance. But because this time we are talking about less than, so I cannot draw the straight line because it's not equal. That means the z cannot be on this perpendicular bisector. So this is negative 2 plus 3i, and this is 4 plus I. So the distance from negative 2 to 3i is less than the distance from 4 plus I to z. So which means we're actually talking about the entire region that is on the left-hand side of the perpendicular bisector. Okay, so if you feel like, oh, why is it like that? So if I choose any point that is here, so you just think about the distance from negative 2 to 3i and the distance of this z to 4 plus I. So that actually fulfills this condition here. The distance is shorter than the distance from 4 plus I to z. So therefore, we need to shade all the left-hand side of the perpendicular bisector. And because this does not have the equal sign, we cannot have a solid line. We must have this dotted line.